Welcome you all. We will discuss aromaticity. In general, one can able to point out that what is aromatic. So aromatic in general, the people are ready to say that benzene containing compounds are aromatic. So in such cases, there are the possibility of non-benzene containing compounds also as aromatic. But as a part of postgraduate level laboratorical identification of aromatic compounds, one can able to point out that ignition testers and nitration testers for the identification of aromatic compound. But theoretically, how one can able to classify a organic compound as aromatic compound, anti-aromatic compound and non-aromatic compound. So in this presentation, we are going to discuss about these aspects. Before going to this, we will have some information about the benzene, the electron delocalization and resonance. So we will talk about the benzene, which was isolated by the Michael Faraday in 1825. This is the simplest and ideal molecule which has the electron delocalization and resonance. So based on this, the performances, the compound is said to be aromatic. And while isolation, lot of debates are going on with finding the structure of the benzene. So Kekul proposed that the cyclic equilibrating structure for the benzene. Later, Paul Sebastier in 1901, who confirmed that it is an cyclic one by converting the reduction reaction, that benzene is converted into cyclohexane. So which confirms that it is an cyclic structure which contains a 6 carbon in a cyclic fashion. Finally, the X-ray diffraction studies, electron diffraction studies, which confirms that benzene is an planar and which has the regular hexagon. Now we know that all carbon atoms in the benzene are sp2 hybridized carbon. And another point of view, the planarity plays a vital role. Planarity of a molecule allows pi orbitals overlap sidewise, leading to delocalization. So what is delocalization means? It is the possibility of new orbital overlapping and additional stabilization to the system. The extra stability or energy gained through the delocalization, which is called as an delocalization energy or resonance energy. So we will see the aromatic compounds. So aroma, the name itself initiated from the odor, which is called aroma of benzene like compounds. And the molecule must be cyclic, planar, with uninterrupted cloud of pi electrons above and below the plane of the ring. This is the prime criteria for a compound to be a aromatic. And it should have 4n plus 2 pi electrons. And we will just categorize that compound according to the German chemist Erich Huckel, who has pointed out that the compound is aromatic, non-aromatic and anti-aromatic compounds. So what is the aromaticity, the definition? The property of cyclohexenes, which can able to produce the nature of aromaticity. So the aromaticity is a property of cyclohexene in which the stabilization of the molecule is enhanced due to the ability of the electrons in the pi orbital to delocalize. Aromatic compounds are organic compounds composed of carbon hydrogen atoms arranged in a ring structure with delocalized pi electrons. So what are the main points that a compound to be aromatic? Aromatic compounds are highly stable due to resonance effect. Delocalization refers to the overlapping of pi orbitals of the adjacent atom. So once the overlapping occurs, the double bonds are conjugated, and the prime rule is it must obey the Huckel's rule, that is 4n plus 2 pi electrons, where the n is the whole number. It may be 1, 2, 3, etc. goes on like this. In general, aromatic compounds are non-polar. So here planarity is different from polar. So this is another criteria that for compound to be aromatic. So these compounds are non-polar. Therefore, they are immiscible with water. And the carbon to hydrogen ratio is less. And these aromatic compounds, especially the benzene containing other compounds also, and substitutions of the benzene, which undergoes the electrophilic substitution reactions due to the presence of delocalized pi electrons. The aromatic ring is rich with electrons, therefore electrophiles can attack this ring to share the electrons. For example, benzene, naphthalene, aniline, anisole, toluene, styrene, etc. can be given as an example. And what is the antiaromatic compounds? So antiaromatic compounds are also a cyclic compounds with a pi electron system, and the pi electron system which obeys 4n electrons in it. Here n is also a whole number, 0, 1, 2, etc. These are highly unstable compounds, thus they are highly reactive. These are cyclic and planar and completely conjugated, but consist of 4n pi electrons only, so that which is never obeys the Huckel's rule. Example, cyclobutadiene. The point to be remembered in the case of antiaromatic compounds: number 1, they do not obey the Huckel rule, that is 4n plus 2 pi electron rule. They are always less stable than the acyclic compounds having the same number of pi electron system. However, antiaromatic compounds have delocalized pi electron system due to the presence of conjugated double bonds. The molecule must be cycled and completely conjugated. So all the antiaromatic compounds are obeys the planarity rule and conjugation cyclic. 3 aspects is obeys. And completely conjugated pi electrons within the ring, and the molecules must have 4n pi electrons, and as usual what we have mentioned that n is equal to 0, 1, 2, etc. Some of the examples that we can able to point out with the antiaromatic compounds. For example, cyclopentadienyl cation, so which contains 4 pi electrons. Oxirene, which also has, see that in the first category you have 2 double bonds. One double bond carries 2 electrons, so that 2 double bonds 4 pi electrons. Whereas in the case of oxirene, a single double bond is there. However, there will be lone pair of electron present over the oxygen. So that can lead to one double bond which is perpendicular only, which adjacent to the lone pair adjacent to the double bond can be considered and perpendicular to the one which will not be considered. So that oxygen will also be the lone pair will be taken into consideration and you have one double bond, so totally 4 pi electrons are available. Similarly with the example of acetylene, here also a double bond is there and nitrogen which has a lone pair of electron. The one double bond and one lone pair of electron can be considered for pi electrons. So here cyclobutadiene, 2 double bonds here in the cyclic form which contains 4 double bonds, 4 pi bonds. And what are the non-aromatic compounds? These are molecules that lack of one or more requirement to be aromatic. That is, being a planar, sometimes it may be a cyclic with conjugation and which fails to obey the 4n plus 2 pi electron rule, or it may fails to obey the 4n rules. Therefore, all aliphatic compounds in general called as a non-aromatic. Even some cyclic compounds which are planar may be non-aromatic due to the lack of complete conjugation. For example, 1,3 cyclohexadiene, which is in cyclic 1, which is in planar, but which fails to obey the 4n plus 2 pi electron rules, and it is an non-aromatic compound. Now come back to the aromaticity. What are the conditions? So there are 4 conditions that pointed out for a compound to be aromatic. Condition 1, the compound must be cyclic. So there will not be a ruled out one, no exception in the case, and it is a straightforward approach that the compound must be cyclic. Number 2, every atom in the ring must be conjugated. That means the pi orbitals presence there which must be participate in a resonance, then only the compound supposed to be aromatic. Number 3, it must obey the Huckel's rule of 4n plus 2 pi electrons with the magic series of n supposed to be a 0, which is 2, n supposed to be 1, it is n 6, like that it goes on 2, 6, 10, 14, 18, 22 with the value of n supposed to be a 0, 1, 2, 3, etc. goes on. And finally the molecule must be flat, which is in planar. The other term is called flat. The molecule is supposed to be a flat one. So I am repeating that one. Conditions are: number 1 must be a cyclic and it must be conjugated. Number 3, it must obey the 4n plus 2 pi electron, and rule number 4, it must be a planar. So we can see that each and every case, if there is a theory may be proposed, there will be some exceptional cases. So here one exceptional case we can able to point out that the compound may follows all the rules and regulations, even then it's supposed to be not aromatic. For example, we can take 10 Annulenes. It is cyclic compound. We can see the structure here provided. It is cyclic, conjugated, obeys Huckel's rule, but due to the presence of trans hydrogens presence there, that is junction hydrogens, which can make the compound is highly repulsive nature, so that due to this repulsive nature the compound is not aromatic and the compound is highly unstable. If suppose we are replacing these two hydrogen by a methylene bridge, What happens now, this methylene bridge which interacting the trans hydrogen or junction hydrogens, because this 2 is replaced by the methylene bridge, so which makes the comfortably the compound supposed to be stable and it is a aromatic. So that the flat nature and the cyclic everything can be compromised with these particular conditions. Now we can see the differences between aromatic, anti-aromatic and non-aromatic. So for a possibility of giving you a repetition on that, aromatic compounds must obey the 4 rules: cyclic, conjugated, 4n plus 2 pi electrons and planar. Whereas anti-aromatic compounds, it is cyclic, planar, not obeying the Huckel's rule, and it may not be flat. Sometimes it may be flat. Non-aromatic compounds which have the lack of either the 4 points that what we have pointed out the conditions. Now we will see the discussions about the differences between aromatic, anti-aromatic and non-aromatic compounds. Aromatic compounds are highly stable, and as equal to this, non-aromatic compounds is also highly stable, because the aliphatic compounds, certain non-aromatic compounds are highly stable, whereas anti-aromatic compounds are highly unstable. And second point is pointing about the conjugation, delocalization. Delocalization, pi electrons are available in large excess in the case of aromatic compounds. Anti-aromatic compounds to have the delocalized pi electrons, whereas non-aromatic compounds having a lack of conjugation may or may not be available the pi electrons to be delocalized. Number 3, aromatic compounds are ready to obey the 4n plus 2 pi electrons Huckel's rule, but anti-aromatic compounds never obey the rules. And similarly, non-aromatic compounds is also not obeying the 4n plus 2 pi electrons rule. And coming to the point of the reactivity, see, compound is highly stable, which implies that it may be less reactive. So that the compound of aromatic nature are less reactive, whereas the anti-aromatic compounds are highly reactive. And as usual, like aromatic compounds, non-aromatic compounds also less reactive. So we can point out 2 examples in each category: benzene and naphthalene for aromatic, cyclobutadiene and pentylene for the anti-aromatic, and 1,3 cyclohexadiene and 1,3,5 hexatriene is an example for this category. Now, so we have the identification benchmarks for compound to be aromatic, anti-aromatic and non-aromatic. Now we can point out with some examples based on that how to predict a compound is aromatic or anti-aromatic. So because of course whether it may obey or not, definitely it lead to the non-aromatic compound. So this is the equation or formula. Simply we can able to say that whichever be the things can be given is a theoretical prediction. A equal to pi b plus electron pair plus 1. So whereas here A is an planar with even number of A value, which implies that a compound is aromatic, whereas A value is supposed to be the overall summation of these pi b electron pair plus 1. The value of A is supposed to be a even number, then it is aromatic. A value is supposed to be odd number, it is an anti-aromatic. So pi b is nothing but number of pi bonds within the ring system. So out of the ring, if suppose there will be a availability of exocyclic bonds available, these bonds never considered as an pi bonds, because according to this prediction we are pointing out the double bonds within the ring system only can be considered. Next one is an electron pair. Number of electron pair outside or adjacent to the ring system can be considered. See that in the category, if suppose a ring which contains anions, so which can also be considered as an electron pair. If it is cation is there, that cannot be considered. So we'll see one by one and we can discuss and point out that the examples. And before going to these predictions, this order of stability and reactivity can just be summarized, then we can go back to the predictions. Aromatic compounds, or the order of stability is highly stable and non-aromatic followed by anti-aromatic, and the order of reactivity is just reverse for that. Now we can see that the predictions, we come back to this prediction that A value can be given pi b plus electron pair plus 1. This is the rule. We can see that benzene ring which contains 3 double bonds. So the pi b is 3. So electron pair outside the above the ring, outside the ring, no electron pairs are there, so the value is 0. So now you can have that increments of 1 can be given for everybody, so that will not be considered. Now we have only 3 double bonds presence there, and we can just substitute in the value. A equal to 3 plus 0 plus 1, which gives you 4. So 4 is an even number, so it is an aromatic. Similarly, naphthalene you can take it. Naphthalene which contains 5 double bonds present in the ring. So that A value is 5 plus 0 plus 1, which gives you 6. 6 is an even number, so once again it is aromatic. Similarly, we can point out that anthracene, just we are giving you benzene to naphthalene, one ring increased and another ring is increased, so that anthracene is 3 benzene rings joined together, so which contains 7 double bonds presence there, and the electron pairs is 0, and we can apply in the formula A equal to 7 double bonds plus 0 plus 1 gives you 8, even number, so that is an aromatic. Then another example we can point out that cyclopropene. So cyclopropene which contains that only one double bond, but see that there is a presence of, you have non-planarity in this. So this non-planarity which leads to a compound which may not be a aromatic due to the presence of sp3 hybridization. So the almost the double bond which focus towards the 90 degrees, so that the corner of this particular carbon, which is an sp3 hybridized carbon, so due to this particular reason, even though it may be containing the odd number or even number, the total things is ruled out. So even though its presence double bond is there, so 1 and 0, and we can calculate it that 1 plus 0 plus 1 which is equal to 2. Due to this non-planarity, this compound is non-aromatic in nature. So we can see another example, that cyclopropenyl anion. The anionic portion which is present there, but in the previous case the same position which anion is not there, that is a sp3 hybridized carbon. So due to this presence of the anionic part which is having a electron pair, which is called as an electron pair outside the ring system. So one double bond is there, one anionic portion can be considered as an electron pair outside the ring, so that 1 plus 1, and there will be increment is another 1, so that 1 plus 1 plus 1 gives you 3, which gives you a odd number, so that the compound is antiaromatic in nature. Whereas the cyclopropenyl cation, so I have given you the examples of the cyclopropene system. So in the examination point of view, the people may generally ask about the cyclopropene system. Plain cyclopropene, due to the presence of sp3 hybridized, it is an non-aromatic compound. Due to the presence of anionic nature, it is an antiaromatic compound, and due to the presence of cationic nature, because that the positive charge which cannot be considered as an electron pair outside the ring system, only the anion only can be considered, so that the only one double bond is taken into consideration and no electron pairs are there, 0, so that 1 plus 0 plus 1 gives you 2, even number, it is an aromatic. So based on that, we can theoretically predict, without doing any laboratory work, we can able to find the compound is aromatic or anti-aromatic. And we can point out some more examples, that cyclobutadiene, which has two double bonds present there inside the ring, and outside there will not be electron pair is available, so A value is 2 plus 0 plus 1 gives you 3, which implies that odd number and antiaromatic nature. And cyclopentadiene, which has, as usual, it is a non-planarity is implied based on the sp3 hybridized carbon, and even though the inside the two double bonds are present, the presence of sp3 hybridized carbon, wherever the sp3 hybridized system is come over there, it spoils the compound of aromatic nature, and it's supposed to be a non-aromatic compound. So in this particular cyclopentadiene, which gives you a non-aromatic nature. And in the previous slide, how we have discussed about the cyclopropene, here we are discussing about the cyclopentadienyl anion, cation, and cyclopentadiene. So similarly, here also the system which is focusing towards the non-aromatic, anti-aromatic, and aromatic nature. So the plain compound is, due to the presence of the sp3 hybridized carbon, it is a non-aromatic in nature. Whereas in the case of the cyclopentadienyl cation, as usual, cation, even though which may have outer surface, the electron pair cannot be considered, positive charge cannot be considered as an electron pair, so that 2 plus 0 plus 1, 3 gives you a odd number, so that it is an anti-aromatic nature. Whereas cyclopentadienyl anion, so the anionic portion implies that, so the sp3 is, if suppose the anionic or cationic portion is not available, then the case in plain compound can be called as an sp3. So here the cyclopentadienyl anion, the anionic portion is considered as an electron pair, two double bonds are present inside the ring, and one electron pair is available, so 2 plus 1 plus 1 gives you 4, even number, so that is an aromatic. And we can discuss about the increased structures of the presence of double bonds. Cyclooctatetraene, so which contains 4 double bonds, and electron pair is not available, so A value is 4 plus 0 plus 1 gives you 5, which is a odd number, so that is an anti-aromatic. But in the case of cyclooctatetraene, if suppose the compound may be existence of tub-like shape or floppy-like shape, so this is availability, In such cases, it is non-planar. So once it's supposed to focus towards the non-planarity nature, once it is come over there, immediately the aromaticity is lost. So that in this tub-like shape or floppy-like shape of the cyclooctatetraene, the 4 double bonds are present and no electron pair is available, and the value of A is, even though it comes as an 5 anti-aromatic nature, but due to this tub-like shape or floppy-like shape of this one, which escapes from the anti-aromatic nature, hence this particular shape of the compound is non-aromatic. So we can able to point out the planarity is lost. Once the planarity is lost, so that the compound, even though the value of uh, odd numbers or even numbers, it may come as an A value, which cannot be considered as either organic, that aromatic compound, or anti-aromatic compound. So which escapes from the anti-aromatic nature, and this is called non-aromatic compound. And we can point out with the calculations of energy is available based on that 18 kilocalories per mole, more stable than the flat or anti-aromatic form of this one, so that most of the cases which can be available as an non-aromatic compounds. And another category, cyclooctatetraenal cation. Cyclooctatrienal cation. Cyclooctatrienal cation. So here 3 double bonds are present there inside the ring, and positive charge is there, cationic portion, but adjacent to the cationic portion, which is called as an sp3 hybridized carbon. So once sp3 hybridized carbon is focused in any kind of the organic compound, immediately we can point out that the compound is non-aromatic. So this is the point of things that one can able to come across with these particular aspects of aromatic or anti-aromatic or non-aromatic compounds. Once it may able to obey the 4n plus 2 pi electron rule. Otherwise, it can able to obey the A equal to pi b plus electron plus 1, and which supposed to get the value of either odd or even values. Even though if suppose they are considering as the odd value or even value, supposed to you get it, if there is a presence of sp3 hybridized carbon is there, then the molecule, the compound leads to be non-planar. So just we'll see about some informations on Annulenes. Annulenes are monocyclic hydrocarbons that contains the maximum number of non-cumulated double bonds. See, like in benzene ring we have 3 double bonds, naphthalene 5 and anthracene 7. Like if you build up like different structures of the single compound which has the maximum number of double bond, then compound is called simply annulenes. They have general formula CnHn when n is even number, and CnHn plus 1 when n is the odd number. So annulenes may be aromatic, which may be non-aromatic, and some cases it may be anti-aromatic. See, we have discussed about the simple organic compounds, and that compound is aromatic or anti-aromatic or non-aromatic, that we have discussed just, and the compound which contains a cationic form or anionic form can also be discussed with the aromatic nature. Now we can see one by one with the annulenes. So this is the generalized nature of number of n values, that even number of values of n implies what kind of the nature of aromaticity it is. So N value is supposed to be 4. It is an anti-aromatic compound. N value is 6. It is aromatic compound. 8 non-aromatic, 10 non-aromatic, 12 is weakly anti-aromatic, 14 is weakly aromatic, 16 non-aromatic compound as proved. We will discuss that in the particular compounds of interest, that and some cases some of the literature mentioned that it's a weakly anti-aromatic. And 18, the N value is 18, is supposed to be an aromatic. So we'll go ahead with one by one. 4 Annulenes. Example of 4 Annulene is cyclobutadiene. It is an 4-member ring with 2 double bonds present there. So we have already discussed this one. Not obeying the Huckel's rule, that compound is cyclic, which has a conjugation, planar, but which is not obeys the 4n plus 2 pi electron, and this compound is supposed to be a not aromatic, but it obeys 4n rule, so that it is an anti-aromatic compound. And coming to the next one, it is an 6 Annulene. Benzene is an example for 6 Annulene, 6-member ring with 3 double bonds present there, which obeys the Huckel's rule, 4n plus 2 pi electron rule, and we can point out that even with the A value gives you 3 double bonds are there, so 3 plus 0 plus 1 value comes to the 4, even number, and this 6 Annulene is aromatic in both the way. So coming to the monocyclic hydrocarbons, 8 Annulenes. 8 Annulenes are polyunsaturated hydrocarbons, and which prefers to be anti-aromatic except to be tub shape like or floppy shape. Already we have discussed on that, which is a non-aromatic. Example of your cyclooctatetraene, 4 double bonds present there, and which obeys in both the category. If you want to cross check with that, whether it obeys 4n plus 2 pi electron or 4n rule, or we can go to the A value of studying pi b plus electron pair plus 1. So either the way we can able to point out that which can satisfy the rules and regulations. Next one is 10 Annulene. You have cyclodecapentaene. So we have 5 double bonds present inside, which obeys the Huckel's rule. So 4n plus 2, n value equal to 2, so that 4 into 2 plus 2, which gives you 10 pi electrons, and it obeys that Huckel's rule, so that the compound is aromatic. And we can able to see another one, which categories in the case of 12 Annulene is an weakly anti-aromatic compounds. 14 Annulenes are again weakly aromatic with the presence of 4 double bonds and obeys the 4n plus 2 pi electron rule, n value equal to 3, 4 into 3 plus 2 gives you 14 pi electrons, which obeys. So in the case of 16 Annulene, 16 Annulene, you have 8 double bonds present there, n value equal to 4, not obeys 4n plus 2, gives you 4 into 4 into 16 pi electrons, weakly anti-aromatic, but it prefers non-aromatic as per the crystal structure studies, proves that it is an non-aromatic in nature. Generally, if you want to point out that in the monocyclic structure of this particular compound, which prefers to be a non-aromatic in nature. Finally, we can see that 18 Annulene. 18 Annulene, we have 9 double bonds present there, n value equal to 4, 4 into 4 plus 2, 18 pi electrons are present there, which implies that the compound is aromatic in nature. So based on some of this discussion, I feel that you can able to point out and summarize the given any number of compounds which can able to see that whether the compound is cyclic or not. First we have to point out that once it is cyclic, now point out whether the compound contains a conjugation is there or not. Once the conjugation is there, now see the whether it obeys Huckel's rule or not. Once it obeys the Huckel's rule, okay, we can give the vote for aromatic nature. Once it is not given by the Huckel's rule, whether it obeys for foreign, then it can go for your anti-aromatic nature. And finally, the compound must be planar. The planarity, the flatness of the compound is definitely into consideration. If suppose the flatness is not available in such cases, the compound, even though it contains and obeys the rules and regulations, but the compound may not be considered as an aromatic in nature. So with these few things, I feel that you may able to point out and notice about the aromaticity of the compounds in clear fashion.